Professor Lee, and to all of the organizers, and good day to everybody, whatever time of day it is there. I apologize, it's still early morning here in LA, and so you get to see the marine layer, but that will burn off here probably while I speak. And I want to start by acknowledging the primary actor in this work, and that is my doctoral student, Mostafa Abu Saida. Incidentally, Mostafa was also an undergrad at Texas A&M Qatar, as was the previous speaker. So that's an interesting connection. And I will go through, a little bit of motivation, but since this is sort of toward the end of the symposium, I think that we've had a lot of that already, and so I will cut to the chase at some point and talk about what we're doing in the lab. Generally speaking, what we're doing is we are cracking methane with sunlight, but in a way that's, in some respects, some important respects, different than what's been done before. And in particular, what we produce is unique and unexpected. So you kind of see that with the deposited carbon picture on the right. So again, I'll just reiterate what people have said over and over. We have a significant global energy problem, and a lot of it comes from the use of heat. And so, I'm a heat transfer engineer. I've been studying heat transfer my whole career, and there seem to be a lot better ways of making heat or capturing heat and using it. And that's part of what we want to do here. And at the same time, we want to minimize the pollution that we create, in particular CO2, which continues to rise in spite of some worthy efforts. In terms of the actual process that we're talking about here, we produce hydrogen. I'll talk about that a little bit, but perhaps more importantly, more interestingly to us, we also produce graphite. On the hydrogen side, this is what really motivated us to start this work. We see a growing market, right? I don't know if hydrogen cars are going to be everywhere or not. That there's a lot of other things that need to happen to make that a reality. But what has been mentioned before is certainly true. The dominant method of making hydrogen today is to use the steam methane reforming reaction. And that is usually a pretty dirty process. It creates a lot of CO2. You can try to capture the CO2. In my mind, kind of people running around trying to catch carbon dioxide molecules and sequestering them and so forth. It seems like, I don't know, almost a fantasy to see that we would be able to do that at scale, but I certainly, it's not my area. I would rather, I guess maybe I'll just pose an alternative. I'd rather catch the carbon before it oxidizes, and that's what we'll talk about today. So one of the reasons, or the main reason, that steam methane reforming is so widely used is that it's cheaper than anything else. And so it's certainly cheaper than methane pyrolysis, if you look on the right side, and today at least it's cheaper than water electrolysis, although there's many great minds working on that, and we've heard from some of them in this conference. If we look just at the methane pyrolysis reaction, right, I like it in particular because it's about as simple a chemical reaction as can be, and since I didn't study chemistry beyond sophomore year in college, it makes me happy. But it turns out there are many intermediate reactions. I'll talk about those a little bit as we go along. But one of the things that we want to do is to eliminate the oxidation, right? So that we don't make CO2 while we make hydrogen. And if you do that, then you can really have a big impact on decarbonization, right? So in terms of how much gets into the atmosphere. Now, I have to preface this. There's been a lot of literature, and this is just sort of one slide on all of the great work that's been done over the years. You can look at the years, going back, almost 20 years, and there's much good work even before that on solar thermal processing of various kinds, in particular for methane decomposition, and we have, I want to pay my respects to all that great work. Our approach is a little bit different, but there's a lot of different ways of concentrating the solar energy, clever optics, and so forth. And I'll talk a little bit about that, and also about what we're doing. But if you look at this table, you'll see that the methane conversion is it runs the gamut, kind of all over the map, on how much of the methane you actually decompose in the process. And then, of course, there's a question of scaling. How large are these demonstrations? Can you do it in the laboratory, and so forth? And is the reaction direct lighting or indirect heating? And people have done a lot of different things. But I'll just pull out that most of the time these temperatures are in the 1200 to 2000 degree Kelvin range, and we'll see that. We'll talk about that as we go through the process. There are a lot of challenges in direct methane pyrolysis. I won't read the slide to you, but you saw before that you have to operate at reasonably high temperatures. The reaction then goes pretty quickly, in many cases too quickly, right? So clogging and wall deposition, window deposition, all of these are big factors that have made direct solar methane pyrolysis difficult in the past. We have some ways of dealing with that, but even for us, sometimes it can be an issue. But as we kind of go down this list, methane pyrolysis, the ultimate form of carbon, is not a single thing. So most of the time, people are making some kind of carbon black, maybe with a little bit of graphitization. If they have graphitization, it's usually because they have a catalyst, right? A metal catalyst. Iron is a typical one. But then you have the problem of separating the catalyst. If you have a big, especially indirect solar thermal reactor, then you typically have a very slow startup thermal response, which means that even if you're operating in a desert, if a cloud passes, you're going to have some issues with startup, or if you have a storm that comes through. And so all of these things are challenges, and that's why methane pyrolysis hasn't been all that active in the area historically, although there's plenty of good work that's been done. I'm going to talk to you about how we approach this, and part of this is to talk about making instrument building that we've done, and how we've built and characterized our instrument. So what we have done is made a custom laboratory solar simulator, and it uses a xenon arc lamp that's very close to AM 1.5 solar. And it's an ellipsoidal reflector, so it has two focal points. We can vary the output current. So the reason that we kind of hand built this thing is so that we could have a very, very tight control on the intensity that comes out of this thing, and we had to build all the thermal systems around it to keep everything cool. Interestingly enough, right, this reactor was actually a product of the pandemic. We started building this after the pandemic began, and so it's sort of, I think of it like a child or grandchild. I had 3 actual pandemic grandchildren. This is the 4th, maybe. But if you look inside, you'll see that all the different things that we had to do to build this. Again, we have at the center of this is the arc lamp. It's a 10 kilowatt electrical input. We get up to about 4 kilowatts of optical output from that. And then we built in a lot of other things to safety and controls. This is the the schematic of the system, and I just want to point out a couple of things. Here's the source, but we have to go through a window, and we have to water cool that window. That's quartz, and then we hit a target. This is very important. So we are, instead of doing some kind of particle flow, suspended particle flow, fluidized bed type of reactor, this is actually hitting a thin target. This target's usually about 3 millimeters. It's porous. I'll talk more about that later. But the nice thing is that by having a geometry in this way, we can actually look at the back of the target. So this is the absorber and the deposition surface, and we can look at that with an infrared camera. And then the flow proceeds out, and we actually do a lot of chemical diagnostics on the exhaust stream, and you'll see a lot of results from that as well as we go through this. Again, I think one of the things we had to do, because we hand built this, was to characterize the actual optical output. And so I'm going to show a couple of slides about that. We did it in 2 ways. Well, really 3. Modeling was the third. But we built a radiometer and used an inverse heat transfer problem solution to determine the distribution of intensity at our focal point on the receiver side. But we also did direct heat flux measurements. That's what's on the right, using a Lambertian target. And so here's the inverse problem, right? And it's important to note, you're going to see this a lot in the talk. We have a very, very large temperature gradient across our thin absorber. And in this case, the absorber is graphite. Later on, it'll be our porous material. But when I first saw that, I thought, oh, that's not very good. Usually in a reactor, you want to have a relatively uniform temperature. But then as we developed results, we found that it was actually a blessing in disguise, because we have basically a one-dimensional flow problem. When we actually flow methane and products through this, it's a very thin material, and so we actually are running many experiments at different temperatures all at once in a single run, having a temperature distribution like this. But for this case, what I'm talking about here is just to basically calibrate our light source. It ends up being best fit by a combined Gaussian-Lorentzian function that's shown on the bottom here. And so we've characterized this again spectrally. We also, when you see 160 amps or 120 amps here, what that is, that's the actual current that's going into our bulb. And so we calibrated all of that so we could find the heat flux distribution as a function of radius. Again, this is a symmetric problem, and you can see that actually our radiometer and heat flux gauge results fall large on top of each other. There's a few nuances because there's some changes in the experiment that we had to make in particular because heat flux gauge is outside of the reactor, so that's characterized outside of the. It's not behind the quartz window, and we had to make adjustments for that. But otherwise, we're pretty happy with the calibration. We also have done a lot of laser absorption spectroscopy of the products. And this is actually done in collaboration with Mitchell Spearin and his postdoc and students. And so laser absorption spectroscopy is what it sounds like. You pick a wavelength that's associated with a particular species like methane or ethylene or acetylene. And then you can especially in a well-stirred reactor or well-stirred product stream, you can get very, very precise measurements of concentrations. And I will show you some of those in a bit. So I'm going to go through and just summarize some of our results so far, and then talk about scale up. So the starting material that I've mentioned a couple of times, so instead of being a flat piece of graphite, which we did for calibration, now we have carbon felt. So this is a porous material made of pan carbon fibers, for those of you who work in composites. and I think it's very, very important for me to say there's no catalyst. Not even the carbon is a catalyst. I'll talk about that later. There's no catalyst in this process. A lot of times when I show this to people that, I'll give a talk like this and they'll say, well, what was your catalyst? Because almost everybody uses catalysts in methane decomposition. We don't have any. There is none. And that's an important feature of this work. Again, at the particular power setting that we used, sort of our default, this is the temperature field on the carbon felt. And so, like I said before, at the center, it's a little bit above 1500 Kelvin, and this is the sweet spot. This is where a lot of deposition happens. And then on the periphery, which is actually the majority of the area, it's a much lower temperature, dropping down to probably at the edge of the carbon cloth. It's 700 degrees Kelvin. So a huge change in temperature across this very thin, it's 3 millimeters thick, porous material. So what we do is we do just a little bit of pretreatment, of thermal pretreatment on the carbon felt. And this is just showing that, basically we go through the process and we reduce some of the material, but it actually starts out in pretty good shape to begin with, but this is just for consistency. But then this was the big surprise. I'm going to dwell on this slide a little bit. What we found is that if you look at the original material, it has a little bit of sort of graphitic content. If you look at some of the, especially the ramen peak, you see these beautiful ramen peaks, and if you then take a cross section, and this was the big surprise, you see that this layered structure. So this is actually very, very high quality graphite. It's probably turbostratic. So this peak, those of you who do carbon nanomaterials, right, it's got a pretty hefty 2D peak, which indicates it's probably turbostratic mostly, but it's not certainly single crystal or pyrolytic graphite. But we also find that that it has relatively high specific surface area, at least for something that looks like it's not porous. This is this is the inside look at it, and so that also indicates to us that it could be useful in, for example, battery materials. Oh, sorry. So I mentioned before that that we have that we can look at this and we have this big temperature gradient. So if we look at the center, this is what the center looks like at the end of a process, right? This is what the original felt looked like, and these are all at the same scale. So there's a very, very, very strong rapid growth rate at the center, but it drops off in about 10 millimeters of radius. So you could think of that as about an inch and a half diameter is the sweet spot. But and we've also varied things like flow rate. We're capturing nearly all of the carbon. Right? If we vary the flow rate through the system, and we go really slow, we're getting almost all of the input carbon in methane is captured by as a solid, and this is based on mass measurements. And that was also a surprise. We had very little of that, of those problems with extraneous deposition on windows and clogging and so forth. It almost all goes on to the cloth itself. It's also very fast. If you look at this, the ramp up temperature goes from room temperature to basically steady state in about 5 seconds. That's going to be useful when you put this in the field and you have a cloud pass or something like that. It's also very repeatable. So we turn the solar source on and off, and this is accelerated in minutes. And there's a little bit of sort of extra curvature to these things because the residence time of the products, that's what we're measuring in this. We're measuring methane in the product stream, and the residence time to get from the reaction site to the sensor, in this case laser absorption, is about 10 seconds. And so that's a lot of that, the slowness is at the bottom is due to that. But it's very responsive and it's very repeatable. So one of the first questions that people have when they see this, and many of my colleagues and people in the community, they say, well, what's going on with the light? Is this just a nice way of concentrating or localizing heat, and then you have your reaction just like you would have it in any kind of thermal process? And it's a good question. What we did, we wanted to see whether there was some kind of photolysis effect, and this is very preliminary still. But so we actually built a shadow mask. It's shown down here, and you see that it has this sort of central circle that's just 5 millimeters in diameter or less. And then we extracted a sample that came out of that process, and we looked at the growth, so the size of the fibers that were as a function of radius from the shadowed region. So this is indirect, and then the directly irradiated parts. And we see a very pronounced effect. Now, you might say, well, maybe that's because the directly irradiated part became a lot hotter, but it turns out, since we're growing basically graphite, the thermal conductivity, and we have some measurements of that, is very high, and we do not expect there to be a large temperature gradient across a fiber like this. In fact, it's almost negligible, which means that the temperature of the fiber in here is the same as here, yet the deposition rate is much higher in a directly irradiated part. And I hope to have much, much more to say about this, because it's something that, as you can imagine, we're studying very carefully. But there is some kind of significant photolysis effect, direct photolysis effect that's happening in this process. I am convinced of that. So I said that we didn't have, kind of clogging issues. Well, what I meant was, if we, for a long time, we don't have clogging issues, but then eventually we get this beautiful coalesced sample. So we start here with, a very open, 95% porous medium. And then after an hour or two, you start to see this. And so we start to choke off our flow, at least in the hot spot. And so we see these degradations of methane conversion and hydrogen and carbon yield. And so so that is a problem. That's an issue for sure. But it's not one that I think is a showstopper at all. And the reason is that we are starting to, we can easily do this process in a roll-to-roll manner. We've done it before with plasma CVD. So what Mostafa did was he built a roll-to-roll system. You can actually see it moving here. It doesn't go that fast. Well, it can go faster than this, but it's actually moving on your screen right now. And so this is just sort of our initial attempt at it. It's done in a different reactor, so we had to kind of change things up in terms of what we had with diagnostics. But we have the infrared camera pointed this way. We do have a viewport where we have a spectrometer that can measure temperature from the bottom. And we had to move some of the laser absorption spectroscopy. But this is our answer to that question, is, putting this into a roll-to-roll process seems like a pretty simple thing to do. When we do it, so you can look at a thin cloth and then the thick felt. We've done it on both. When it rolls, so we start out and we kind of see that not clogging, but decrease in porosity, and that kind of drifts our conversion and yield down. And then we start rolling it, it comes back up, so on and so forth. These numbers are lower because there's a lot of bypass flow in the way that we set this up in terms of conversion and yield. But the same thing happens for thin or thick. And so we think that this is very much a viable way to go through the process and to scale it up. And I should say that we're going to put in a paper for for the conference that really talks a lot more about the roll-to-roll scale up of this. So there's a lot of things, as I mentioned earlier. This is very new. It's not something that we've been working on a long time. We're kind of a newcomer to the field, in fact, at least of methane pyrolysis. There's all kinds of questions about photocatalysis. We're studying them with wonderful partners. We are working on optimizing process conditions, which is something we've done for carbon nanotubes and graphene synthesis, usually in plasma CVD, using advanced data science approaches. And then looking at how this graphite, which by the way is very, very close to pure graphite, the kind of mined pyrolytic graphite or mined graphite and refined graphite that you'll find is that dominates the lithium ion battery supply chain right now. So we're looking into that. And then of course we need to figure out if this thing is economical, as I mentioned up front. If you just think about hydrogen production, right? The reason that people use the dirty process is that it's the cheapest, and so that's ultimately in a field, a market that's so big. The energy market is, the biggest market, always will be. You have to win on cost, and those are very important questions to answer about that. Here's just an example of some things that we've done to start on the optimization question. This is a Bayesian approach that we used for making graphene and optimizing pressure and optimizing the power of the system, and we're applying these principles to that. We've also, and this gets back to the question of catalysis, we've grown now this graphite on lots of different materials. So the starting carbon felt, again, I mentioned it was pan fibers. It's basically irrelevant. All you really need in this process that we found is a felt material or porous material that can withstand the temperatures of the process. So we put it on all these different oxides, and we get the same thing. So I apologize that for those of you who don't read Raman charts, but all these Raman results say that this is the graphitic peak. There's a defect peak that's here that varies a little bit from material to material, but they all have this 2D peak, which indicates also good graphitic quality. So this process seems to be pretty agnostic to the starting substrate, and that's also potentially a good feature. And then on actual field scale up, getting out of the lab, instead of having a solar simulator, we will have the actual solar source itself. Right, here we are at UCLA. The California Energy Commission is launching a project with us or for us where we will actually demo this out in the desert a little bit past Palm Springs. And that's just starting up now, and we're excited about that. And there we'll use a dish concentrator and a receiver that we'll have to design and build. And so with that, I think I stayed pretty well on time. I just wanted to thank you for your attention. I think that this event has been fantastic, and I appreciate all of the speakers, all of the attendees, and I will be happy to take questions. Thank you very much.
Great, thank you, Timothy, for the great talk. I think we have a question from Ju.
Thanks, Professor Fisher. This is super exciting. You focused mostly on the carbon product, but how about the hydrogen yield from the process?
Yeah, so it's almost psychological. Like you've analyzed me. We started out doing this, as I said, trying to make hydrogen. And let me go back to a chart. I'll go back to kind of the one. So we get about this is as good as any. So the hydrogen yields that we're getting, again, and you have to take it with a grain of salt. We have this this huge. So all the reactants are flowing through this porous medium, and so we only have a sweet spot in the middle. But even so, the hydrogen yield is up here above 70%, right? So even with all of that bypass, we're getting 70% conversion of the total input, which is surprising to me. In fact, I'm thinking that there may be some, I worked in free convection. There may be some density changes that's actually channeling flow toward that middle thing, where the temperature is higher. We haven't done a full CFD simulation of it yet, but that's a surprising number, surprisingly high number. We are, of course, working on making this. So this looks like a bullseye now, making this much more uniform in temperature. And then we expect to have hydrogen yields that will probably be in the 90%.
Yeah, this is very good. And then you mentioned this turbostratic disorder in the graphitic carbon. I think the battery people and the supercapacitor people have different demands on the amount of disorder in the graphite. I think for lithium-ion battery anode, maybe they don't want to have so much turbostratic disorder. But I think for fast charging and discharging, and maybe for sodium-ion battery, they could want to have more of this rotational disorder. So have anyone evaluated this carbon material in that kind of energy storage setting?
Yeah, so we've started to look at it with lithium ion, so just a half cell, just the usual lithium half cell, and it is close to, it comes close to the theoretical capacity of graphite.
Okay, that's great.
And so we were thrilled about that. That's another thing to stay tuned about, and we're trying to optimize that. Another thing that we need to do with the battery kind of raw materials market, right? We have to find other materials as starting materials, right? So even though pan fibers are kind of the lowest grade of carbon fibers and kind of cheap, it's still expensive to get a carbon felt made of pan fibers, right? It's actually a pricey. You can compare it to how much you can actually sell graphite to battery makers. So we need to find some other things.
But I mean, once you produce this substrate, cannot you just keep using it? Like you can just keep growing on it?
Yeah. So I mean, can you? So the question is, can you then release the graphite and then reuse the substrate? We're thinking about that in a couple of contexts, but in the if we start with carbon, probably we would just surely those pan fibers also are graphitized because they're actually sitting, they're getting hot. And so we wouldn't do it for that, but maybe for some of the other ones, but that takes more post processing and separating. It's like using a catalyst, which we love the fact that we don't have any catalyst. In fact, people who worked on methane pyrolysis, spent their whole careers doing it. When they see this, I talk to them, they say, well, how can you do this without a catalyst? It's maybe they could see you could do it, you could get carbon black or some very low grade carbon, but the fact that we're getting this beautifully ordered graphitic product is a big surprise to people in the field. And it's been done before to some extent, but only with the catalyst.
Fascinating. Thank you.
It's just following up with this. You mentioned this very surprising effect when you speculate that it's direct photolysis effect there, right? Rather than just the thermal effect. So can you just add a bit more speculations along this direction, right? So it's kind of also surprising to me that in the shadow area and the direct light area, right? So there's a big difference of the diameter. Yeah. So is it like speculation to satisfy our curiosity here?
So here's my speculation. I don't. I'm too old. Like I told you, I've got grandkids. I'm told to persnickety about things that I'm thinking about. So here's what we think is happening. We think that as the methane approaches the porous absorber deposition substrate, right? It's heating up. There's translational energy exchange, molecules colliding, and so forth. So it heats up and it starts to react a little bit upstream, but the actual residence time in the reaction zone of methane is only about 50 milliseconds. So everything needs to be really, really fast, especially to get these kind of growth rates. We think what's happening is that there's a partial decomposition. probably very much like how a soot particle is formed. And so you have these gas phase molecules, intermediate molecules, that absorb light directly. And so then that intermediate reaction going from methane to these intermediate soot precursor type particles, they get heated. They have absorption lines that can be accessed certainly with the broadband solar input, and then they are probably heated beyond the local temperature because of that absorption, and so their kinetics accelerate. That's what we think, and then the whole reaction goes faster. That's what we believe is happening. We think it's actually more pronounced than even this graph would show, because remember, all of these things, so everything that you see here is being constantly exposed to light, and it's at high temperature. There's surely some kind of annealing that's happening, and probably little graphene domains that form here will be able to kind of diffuse down a little bit. So we actually think the effect is even more pronounced than what's shown in this graph.
Great, thank you. Yeah, so that's interesting, very interesting. So maybe in the end, let me just ask a high-level question, right? So you talked about hydrogen production, and also some the previous invite speakers also talked about this. So what is your vision about it? Also talk about the hydrogen production cost. So what is your vision about hydrogen economy, right? People talk about using hydrogen storage to drive or power the electric vehicle, right? So there are also many other application scenarios. So in order to put hydrogen into a commercial product in the future, what do you think is the most promising application scenario, and what is the highest barrier to commercialize?
Yeah, I'm not a policy person. I work with policy people a little bit. I listen to them a lot. I've known many people who have been kind of leaders and thought leaders in the hydrogen economy. And I would just say this, just from I don't know, I'm a technical expert. I'm really a researcher at heart. I think that stationary power for hydrogen makes a lot of sense. I don't see it for mobile power, right? Nearly as much. It just seems, you all know, you know all the reasons, and I'm not saying that it won't happen, but from just my sense as both a scientist and a consumer, I think stationary power looks very compelling for hydrogen, and you could make the electricity and the losses are reasonable, and then you electrify as much as you can beyond that. That's what I think, right? That's just my opinion. So
great, thank you. Yeah.
Maybe add to that is that how do you envision this? Because eventually we could use methane for seasonal, energy, and then this could be, put into individual homes, right? So, at what sort of a scale do you envision this technology could be applied?
Yeah, it's a great question. So we think that this will be fairly easy to distribute. So you could imagine, let's just run the scenario where hydrogen is used as a transportation fuel. You could imagine, every service station pretty much in the country has a natural gas line hookup, right? You could imagine a fueling station that would just take that natural gas line, have one of these reactors or 2 or 10, and actually make hydrogen on site. They'd have to do a little bit of separation at the end, surely, but then you could have it distributed that way. You could also do things like blending. Like a good example that's been presented to me is, if you take midstreamers, so there are all these big natural gas pipelines that are moving natural gas around the country. You could bleed off some of that, convert some of it to hydrogen, put the hydrogen back into the line. So now you have this blended methane hydrogen mixture, and then you take the carbon that we're making here and you do something else with it. It's important to understand in terms of cost. People ask, well, what is the hydrogen cost going to be? for something like this if you scale it up. You know, to me, that's, I don't even really think about it. For every 1 kilogram of hydrogen this process makes, it makes 3 of carbon, of graphite. And the graphite can be sold, you know, in lots of different markets at a much higher price per kilogram. And so now you've got these 3 units of carbon that you make that you can sell for, that somebody can sell for more money. And then the hydrogen is just like an afterthought. It's like gravy. And it could be done very cheaply then, I think.
I look forward to using this gravy to heat up my furnace in the winter.
That sounds good to me.
Yeah, great. Thank you, Timothy, Professor Timothy Fisher.